go in package, Hypergeometrica. I'll keep this stuff here. And let's try loading it. So restart. Let's remove our system index and do all quick load. All right, what are the errors in bit reversal? Fixed num safety fell through. So let's see, as fixed num safety. I wonder if they remove this. Doesn't matter, we can hash plus ignore for now. What else was there? Fixed num safety. Let's try reloading. Okay, it loaded. Alright, so are we in the correct package? Yes, we are. So let's go back to our number theoretic transform. So like I said, ideally we choose a modulus, which is as close as possible to our fixed num width, or our, well, in Lisp they're called fixed nums. Reason being, we want to use as many of the bits of the fixed num as possible. So I wrote these functions to compute a modulus, which is suitable. There are actually some other things that are needed for the modulus. Like I said, we need inversion, and we need if we're computing a Fourier transform of length 1,000,000, we actually need our what do you call it? The modulus to be co-prime with that, because in the end we need to do a division. But if we have inversion for all elements, then this is trivially satisfied. But it's just a note that our modulus doesn't necessarily need to be prime, as long as we have a field and as long as it's co-prime with our what we're dividing by, and we're dividing by the total transform length. So if I go into Hypergeometrica, and I do, let's try print suitable moduli. Let's do a transform length of 1,000, and let's try finding 10 things if possible. So here we get, I'll make this a little bigger, 10 possible things. This column right here, you probably can't see on my screen. This column is the modulus. Following up is the factorization, and then the things on the left right here, as you can see in the documentation. The first number is the width of the word needed to represent this integer. And then the next number is the number of wasted bits that we have. We define a wasted bit as something that we can't use for the transform length. So we want to maximize this first number, and we want to minimize this this second number. So of these transforms, of these moduli right here, this is pretty good. 14 bits, which is within our word limit, and then we only have 2 wasted bits. That's really nice. This is a very, very large power of 2 multiplied by only this little 3 right here. On the other hand, we have kind of bad things. A bad one might be this right here. We have 16 bits that are needed to represent this number right here, but 6 of those bits are wasted. So let's instead look for numbers around, let's say we want to do a billion. So 1,000, let me do this again. 1,000, million, billion. 1, 2, 3. Yep. Okay, so we're saying we want to do a number theoretic transform of length 1 billion. Practically speaking, that means we want to multiply numbers that have 1 billion digits to them. That's actually not quite true. It's actually more than a billion digits because we can take advantage of the fact that each element in our transform is representative of some number whose base is 0 to our modulus. But anyway, it's more or less equivalent up to some constant factor of a number with a billion digits. So when we do this, we get the following. Really, really kind of nice properties. Here, we see that there are lots of wasted bits. Most of these have 6 or 7 wasted bits, but here's one that's kind of nice, 4 wasted bits only. So for a 37 bit number, we can use this modulus right here, 77309411329, whose factorization is 1 plus 2 to the power of 33 times 3 to the second. We can use this as a modulus in our number theoretic transform, and we're only wasting 4 bits, so our transform length is satisfied and everything. The nicest one of these, however, if I was implementing code in C, would be this one right here. This is a very nice number because it's 32 bits long, which fits into a typical 32-bit integer. There's only 2 wasted bits, so of our 32-bit integer, we can have up to 2 to the 30, which is perfectly adequate for this 1 billion length. And the factorization is nice. It's just 2 to the 30 times 3, plus 1, of course. So this would be a very exciting transform to use. Now, the catch of sorts is if we're working in the field of integers mod some modulus, going back up to our multiplication, if I go back to m times, it's possible that this can overflow unless we implement it better. And I started implementing it better by doing fixed width multiply, meaning if you have 2 numbers a and b and you have a limit of width bits, then what this will do is do the multiplication and ideally return 2 values, one value being the high order bits and the other value being the low order bits. But until that's implemented, we have this issue of overflow. So this puts a limit to the base that we can select for our arbitrary precision numbers. I don't think it's worth going into too much detail about that right now, but it's important to note. One sort of interesting thing that we can look at now is looking at kind of our maximum representable moduli in an efficient fashion. So let's look at transform lengths that are, let's say, 1 trillion or something. 1, 2, 3, so 1,000, million, billion, trillion. So we could do trillion-digit transforms just fine, using only 47 bits. Again, we have some wastage, 43 bits with only 2-bit waste. Let's kind of look at 100 of these. Yeah, there are plenty to choose from. It's not exciting to see 10 bits being wasted here and there, but sometimes we'll find a really lucky one. This is a fun part of experimental mathematics, in my opinion, is that you have this scope and you can look at all these things. If we were to kind of very theoretically try to think of these prime numbers that we can use, it'd be very difficult to construct a mathematical framework, I believe, to find good moduli. But when you have the power of a computer, you can just search for them, and it really feels like an exploratory thing. So there weren't any really good moduli, actually. I mean, we had this really good one at the top originally, this 43.2, but all these other ones are just kind of okay. I mean, we kind of have this one. That only has 4 bits of waste. I'm scanning through and I don't see any other good ones. All of these have 9, 10, 11 bits of waste. What about for higher number, 10 trillion? Yeah, again, nothing that good. So I built in this thing to this function, to help the search that allows us to tell us how many bits we want to waste. So max waste. We only want to waste, let's say, 5 bits at most. And it gives us a pretty good list. Let's say we want to waste only 4 bits. It narrows it down, of course. Sometimes we have to search for a lot more, and we get a few more. Here we found 2 more, which are very good. Let's use the full range of our 64 bits, and let's look for just 10 times more. It's going to take a little bit. And we see we did not find any. I mean, so these things, they're abundant in some sense, but they're not so abundant that you can find lots and lots and lots of them. 58.3 is incredibly good. That's a very, very good number. While I'm talking about other code, I'll do another search. I'm going to double this while it searches. So there are these other things, kind of other auxiliary functions deal with prime numbers and so on. Actually, right here is a search, a really nice one, where we found some good things. This is the 58.3 that we found already down here. Again, it didn't find anything. And then we found some of these other ones that use up to 62 bits, but they all have a lot of waste. So we have these other functions that compute it, and I have some test functions here that compute the multiplications of 2 numbers, using these methods. So I'm seeing, yep, we have multiply here. So let me try that. Multiply 1, 2, 3, 4 by 5, 6, 7, 8. When we do this, it gives us, we're multiplying these 2. We break them out down into digits, but we make the transform length the power of 2, padding with zeros. We find our modulus and our primitive nth root. We find a number of theoretic transforms of these, and we get our final result, which is this. The big question is that actually the product? And indeed it is. So I think I've harped on number theoretic transforms enough. The last thing is, if we can't find transform lengths that are large enough, we may opt to use so-called Chinese remainder theorem, which says if we do all of our arithmetic mod m1 and do all of the same arithmetic, the exact same arithmetic mod m2 and so on for n moduli, it's amenable to combine all of those to find the same value of x under this composite modulus m1, m2 to mn. So what that allows us to do is if we're multiplying really, really, really long numbers, we can do the multiplications of those long numbers with smaller moduli, and then at the end, using Chinese remainder theorem, compute them together. So back to the pi computation. Essentially, we want to use this number theoretic transform machinery in order to compute pi. Before I move on, I want to just check something out. Okay, we've been at an hour and 13 minutes, so what I'll do is I'm going to try to start abstracting things and start thinking about how we'll write code for doing this on a cluster. So the ideal aspects of a cluster are that we can distribute computations in parallel, and all these clusters will work hard to compute these computations. Then when they're done, they send their result back to one of the main nodes, and then the main node does the job of actually of combining the results in different ways. So we have to think about how we can take all this code, which is all done in memory right now, just normal memory, how we can parallelize it, how we can distribute work units, and so on. So let's go back to our binary splitting. Like we said, binary splitting is going to be the main workhorse for how to compute series. In our distributed computation stuff,